Welcome to this week's third lecture. In the last lecture we have seen the concept of invariance, and also we have seen the eigenvalues and eigenvectors of matrices. So today we are going to learn how the concept of invariance is going to be useful for us to be able to obtain some simple matrix representations for linear transformations. So let us first remember what invariance was. So if I have a matrix X which is in Cn by n, and suppose that I have also the space V is equal to Cn. In this case, A is a linear transformation from V into V. Okay? So I have V here, and A matrix is a linear transformation from V into V. And suppose that I have a subspace M of V, and this is both in the domain and the codomain. And I call this subspace M invariant under A if all vectors in M are transformed by A into other vectors, or the same vectors in M again. Okay? So here the concept of invariance can be summarized with a single statement. It says that it is A times X is always in M for all X in M. Okay? Whichever vector I transform from M, that vector is transformed into M with the linear transformation A. That is the concept of invariance. And we have also learned that null space of any polynomial of A is invariant under A. Okay? So if I take any vector from the null space and if I transform it with A, I would get another vector inside the same null space. Okay? Is invariant under A. So this is going to be important in obtaining basis sets to obtain some simple matrix representations. Okay? And then we have seen the eigenvalues and eigenvectors. So remember, we define a polynomial D of S. It is called a characteristic polynomial, and it is determinant Si minus A. And this polynomial is the characteristic polynomial, and the roots of this polynomial, so roots of the equation D of S equals to 0 would give us the eigenvalues. Lambda 1, lambda 2, they are all the roots of this equation. And what about eigenvectors? If I have the equation A times EI is equal to lambda I EI, when satisfied, when EI is not equal to 0, then EI is an eigenvector of A with corresponding to the eigenvalue lambda I. Okay? Eigenvectors are by definition non-zero vectors, and for each eigenvalue there should at least be a single eigenvector. Okay? So we have these concepts now in our use, and now we can use such concepts in order to be able to obtain some simple matrix representations for linear transformations. Okay? So remember, we have started with an example, and we have solved some of it. So I have A equals to 2, 1, 1, 2. It is this matrix. And suppose that I find this matrix to be complicated. It has only 4 elements, but let us say that it is complicated. And suppose that I would like to change the basis sets for the domain and the codomain of this linear transformation to obtain some simpler matrix representation for the same transformation. In order to be able to do that, we are going to use the concept of invariance. Okay? And this concept is going to allow us to select basis vectors for the domain and the codomain of this linear transformation. And when we select those basis vectors cleverly, then we are going to see that we will be able to simplify this matrix with a simple matrix representation. Okay? So remember, in the last lecture we have found the eigenvalues of this matrix. Lambda 1 is equal to 3 and lambda 2 equals to 1. Okay? Now, I have found eigenvectors last time. The first eigenvector corresponding to 3 was 1, 1. And the second eigenvector was 1 and minus 1, corresponding to the eigenvalue lambda 2 equals to 1. Okay? Now, We talked about the null spaces last time. Null space of A minus lambda 1 identity. This was the span of the first eigenvector, 1, 1. And null space of A minus lambda 2 identity was the span of the second eigenvector, 1, minus 1. Okay? These are our eigenspaces. And do you think these are invariant spaces under A? These are two subspaces. And do you think they are invariant under A? The answer has to be yes here, because these are null space of a polynomial of A, null space of a polynomial of A. So they should be invariant under A. Okay? What about the dimensions of this? Dimension of this one is 1. And the dimension of the second null space is 1, because their basis vectors are composed of only one vector, one linearly independent vector. So their dimensions are 1. What happens when I sum these null spaces? Null space of A minus lambda 1 identity plus null space of A minus lambda 2 identity. The question of sum of two subspaces, what does it mean? It means that which vectors I can obtain as the sum of two vectors, one from this null space and the other one from the other null space. So what type of vectors can I obtain by taking one vector from this subspace and another vector from the second subspace, and when I sum them? The answer is going to be, since these vectors, the basis vectors are linearly independent, it's going to be the whole C2 or the whole R2 you can write here. Okay? So the sum of these two subspaces is C2. Okay? And because the basis vectors are here linearly independent, this is actually a direct sum. And I have a third property here, but I really do not like to use it now. And in this case, that property is that the basis vectors of these two subspaces are orthogonal to each other. Okay? That means that this is actually an orthogonal direct sum. And in the future parts of this course, we are going to see that symmetric matrices or Hermitian matrices would always have such a property. When the whole space can be written as the orthogonal direct sum of the eigenspaces for symmetric or Hermitian matrices. Okay? So this orthogonality is also a property of the symmetric matrix. And the dimensions here are 1, 1, and dimension of C2 is 2. Okay? So there is no redundancy, dimension redundancy here, because we have linear independence of the space, because this is a direct sum. Okay? So here, how can we use such a property in order to be able to obtain some simple representation or simpler representation for A? I know that this A is a linear transformation, and it is given like this. Y is equal to AX. So when you have such an equation, in this equation, X is in the domain and Y is in the codomain. Okay? And what are the basis sets for the domain and the codomain? And when here in this equation, I don't really see any basis set. Okay? That means that here in the domain and the codomain, we are using the so-called canonical basis sets. Okay? What does that mean? So canonical basis set for C2 is this basis set, 1, 0, and 0, 1. Okay? And when no basis sets representations are written here, you have to assume that the default basis set would be the canonical basis set, which is given like this. Why is that? So suppose that I look at a vector x, and let us say that this vector x is composed of elements x1 and x2. Such a vector is always equal to its representation with respect to the canonical basis set. Okay? What do I mean? What is the representation of X with respect to the canonical basis set? Okay? This is the representation of X with respect to the canonical basis set. Okay? In order to be able to find this representation, I need to express X as a linear combination of the basis set elements. Okay? Let us express the vector x1, x2 as a linear combination of the basis set elements here. 1, 0 plus 0, 1. Okay? And in this case, the coefficients, as you see, should be x1 and x2. And these coefficients would give us the representation of x with respect to the canonical basis set. Okay? X with respect to the canonical basis set is equal to x1, x2. But this is x itself. Okay? So as a result, we see that each vector in C2 is equal to its representation with respect to the canonical basis set in C2. Okay? So when you have an equation like this, you have to maybe you can understand it, or you can interpret it like this. Y with respect to the canonical basis set is equal to A, x with respect to the canonical basis set. Okay? It's the same interpretation. All right? And then A becomes the matrix representation of a linear transformation, and where both in the domain and the codomain we are using the so-called canonical basis set. All right? So now what I would like to do is I would like to obtain a simple matrix representation for that linear transformation. Okay? And in order to be able to do that, I will change the basis set in the domain from the canonical basis set into another basis set. Okay? I will choose my basis set to be as follows. It is going to have again two elements because we are trying to find the basis set for C2. And the two basis vector elements are going to be eigenvectors. Okay? So I would put the eigenvectors here, 1, 1, and 1, -1. So our basis set is composed of the eigenvectors E1 and E2. Then I'm going to try to change the basis both in the domain and the codomain for this linear transformation, and I will obtain another matrix representation for the same linear transformation. Okay? So I will obtain a new matrix representation A bar for the linear transformation A, and I would have x with respect to B here. So the question is, what is this A bar? Okay? When we change the basis in both the domain and the codomain from the canonical basis set into this basis set B, which is composed of the eigenvectors of the matrix A. Okay? So remember, we have a procedure for making such a basis change. Okay? Here is what I'm going to do. I'm going to use this equation in order to be able to find this A bar. And I will find A bar column by column. I will first find the first column of A bar by choosing a specific X and then specific Y. And then I will find the second column of A bar by choosing another X. The first X that I'm going to choose is going to be this X, the first basis vector. Second X will be the second basis vector. So our procedure will be simple. Choose the first basis vector as my X, and then find the first column of A bar, and then choose the second basis vector as X, and find the second column of A bar. Okay? Let us apply this procedure. So if X is equal to the first basis vector, 1, 1. This is my eigenvector. Remember, this is E1. Okay? What is Y? Y is going to be transformation of X with A. Okay? So, and I have here just A is equal to this matrix times the vector 1, 1. When I multiplied matrix A with the vector 1, 1, that means that I will sum the columns of this matrix. It is going to be 3, 3. But this is 3 times the basis vector 1, 1. Because this vector was an eigenvector actually. Okay? And now let us write the representations of X and Y with respect to B. We are going to use this equation to find the columns of A bar. So X represented with respect to B. So this vector is the first basis vector. So if I want to find the representation of this vector with respect to these basis vectors, I need to express this vector as a linear combination of the basis set elements, and I would write the coefficients as my representation. Okay? 1, 1 is nothing but 1 times 1, 1 plus 0 times 1 minus 1. So the representation of x with respect to b is 1, 0. What about representation of y with respect to b? Y is 3 times the first basis vector. Okay? Therefore, the coefficients of y, when I try to express it in terms of the linear combination of these two vectors, the coefficients will be 3, 0. Okay? This is a representation of y with respect to the basis set B. Okay? Now, let us use that equation there in order to be able to find the column of A corresponding to this. So y represented with respect to B is 3, 0. That is equal to A bar times x represented with respect to B. X represented with respect to B is 1, 0. Okay? And I know that when I have A bar given like this, and when I multiply it with vector 1, 0, I know that this is going to give me the first column of A bar. Such a matrix vector multiplication gives me the first column of A bar. Okay? That is equal to the first column of A bar. Okay? So what does this mean? First column of A bar should be 3, 0. Okay? So if I try to write A bar, then it is going to be, first column is going to be 3, 0. All right? Now we come to the question of what is the second column. And as you know, in order to be able to do that, I will choose my x, 1 and minus 1, the second basis vector. Let us choose x equals to 1 minus 1. And in this case, what is y? Y is A times x. 1 minus 1 times this matrix means that I need to subtract the second column from the first one. Okay? Subtract the second column from the first one. And it is going to be 1 minus 1. Okay? But this is this x vector itself. So now let us write representations. X with respect to b. This is my second basis vector. So when I try to express that x as a linear combination of these two vectors, coefficients would be 0 and 1. Okay? This is 0, 1. And y represented with respect to b should be the same. Okay? And when I write this type of equation in this case, I would have 0, 1, y represented with respect to b, and that is equal to A bar times x represented with respect to b, 0, 1. And we know that this is going to give me the second column of A bar. Okay? This matrix vector multiplication is going to be the second column of A bar. Okay? And that means that my second column has to be 0, 1. Okay? So this is our A bar now. So our simple representation corresponding to this matrix here, this symmetric matrix, turns out to be a diagonal matrix 3, 1. And the diagonal elements are nothing but the eigenvalues of the matrix. A bar is 3, 1. When we change the basis, we obtain just this. And I know that this is lambda 1 and lambda 2. All right? So in this case, we have a diagonal simple representation. Our initial matrix was more complicated, and our simple representation has more zeros than A itself. Okay? In general, in many cases, we will be able to do this if the matrix is so-called diagonalizable. So we will be able to choose a basis set, and we will be able to change the basis in both the domain and the codomain to that basis set. And then we will obtain a simple representation for the linear transformation, which is going to be diagonal. But in some cases, we will see that this is not going to be possible. For non-diagonalizable matrices, we will see that this is not going to be possible. But in those cases, we will see that we have a simpler representation that is very close to a diagonal matrix. It will have lots of zeros, but it would be close to, it won't be a diagonal matrix, but it would be close to a diagonal matrix. Such a matrix form is called the Jordan canonical form, and actually we have just started our journey towards that simple form, the most general, simpler representation that we can find for any matrix. Okay? So here, I would like to do this operation. I would like to explain this operation in terms of some matrices. So I would like to write this A bar, this simpler representation as a function of A. What would be that function? Okay, I would like to write A bar, this simple matrix, as a function of A. So I would like to relate this A bar to A using some expression. Okay? How can I really do that? So here I will start with the following equations. A times E1 is the lambda 1 times E1, but lambda 1 is 3, so I have 3E1 here. And the second equation that I will use for this purpose is A times E2 is the lambda 2 times E2. It is 1 times E2. Okay? Here is what I'm going to do. I will write these equations in the reverse. Okay? AE1 and 1E2 is equal to AE2. Okay? So in both sides of these equations, I would have column vectors with 2 elements. And now what I'm going to do is that I will collect the right-hand sides into a single matrix. These are the column vectors, AE1 and AE2. I will put those column vectors into the columns of a single matrix. Okay? And then I will do the same thing for the left-hand side as well. Okay? 3 times E1 and 1 times E2. Okay? So now these are 2 by 2 matrices on the left and on the right. Okay? So now I have the columns of a matrix, E1, E2, is multiplied by A. Both columns are multiplied with the same matrix. So I will write this matrix as follows. This is A times the matrix composed of the columns E1, E2. Okay? This matrix, A times the matrix composed of the columns E1, E2 is this matrix. The first column of it is AE1, the second column is AE2. And I will call this matrix as the matrix P, our basis change matrix. Okay? So this is, as you see, a matrix which is composed of the basis vector elements. Our basis set element. Our basis set was composed of E1 and E2. Okay? So we put the basis set elements as the columns of a matrix, and we call that matrix P, which is the basis change matrix. All right? Then I would like to write the left-hand side as well in terms of the matrix P. Okay? So I can do that as follows. This is the matrix P, E1, E2, and I will here put another matrix. Okay? On the left-hand side, the first column should be 3E1. Okay? So when I multiply the first column of this unknown matrix with this matrix P here, the result should be 3E1. So you see that here into the columns I need to put such coefficients that the result of the multiplication is going to be 3E1. So here I need to put coefficients 3, 0. Why is that? Because the first column of this multiplication would then be 3 times E1 plus 0 times E2. And that would be 3E1. Okay? And what about the second column? The result of the multiplication of the second column of this matrix with this P needs to be 1 times E2. Okay? In that case, what should be the second column here? It needs to be 0 times E1 plus 1 times E2. So therefore, the coefficients should be 0, 1. Okay? So you see that unknown matrix there, this is nothing but my A bar matrix, our new matrix representation for the linear transformation. Okay? So this matrix P is actually always an invertible matrix because it is composed of some basis vectors of Cn. This P is always going to be invertible, and that is going to give us the following equation. P times A bar is A times P, and if I take this P to the other side, then that is going to be A bar is equal to P inverse AP. Okay? So this is our basis change formula. You might remember this formula from the earlier parts of this course. You have seen that in the case of the matrix representation of linear transformations, if you want to change the basis in both the domain and the codomain at the same time, from the same basis to another basis, to a common basis, you would get this formula. Okay? So the rest of the course actually is going to be related to this formula. So it is very important to actually understand what this formula is doing. It is changing the basis from the canonical basis set into a basis set given to us. And the columns of this matrix P would always contain the elements of the basis set. Okay? So now using this equation I can write what A is. A is P times A bar times P inverse. Okay? So now here is what we are going to do. We are going to try to generalize this idea a little bit. In this example, we had C2 equals to null space of A minus lambda 1 identity plus null space of A minus lambda 2 identity, and the dimension of these invariant spaces were both 1. Okay? And then what did we do? We have put some basis vectors into a matrix P, and then we have obtained a simpler representation. Our simpler representation is diagonal. What does that mean? That means that we have a block diagonal matrix with 1 by 1 blocks. The size of the first block is 1 by 1, and the size of the second block is 1 by 1. Okay? Which are the same as the dimensions of these invariant spaces. Okay? Now we're going to try to generalize this idea, starting with a decomposition of Cn into some subspaces which are invariant under A. If we can find such a decomposition of Cn into some invariant subspaces under A, then we will be always able to obtain some block diagonal matrix representation, simple matrix representation, which is block diagonal, where the sizes of these blocks are going to be the dimensions of these invariant subspaces. Okay? So we are going to now see the generalization of this simple example. So let us now write this generalization as a theorem. Consider the linear transformation y is equal to ax, where a is in Cn by n. In the earlier case, n was 2, and x and y are in Cn. Okay? Now suppose that the first condition is I can decompose Cn into a direct sum decomposition, M1, M2, of some subspaces, Mk. Okay? These are our subspaces, K subspaces. And let us suppose that, secondly, each subspace, Mi, is invariant under A. Invariant under A. Okay? In the earlier case, we have decomposed C2 into two subspaces, which are both invariant. Okay, M1 and N2. And in that case, our A bar was block diagonal with blocks 1 by 1. The rest is equal to 0, which has the dimensions 1 and 1. Okay? Then, the transformation A has a block diagonal representation. This A bar is in the following form: A1 bar, A2 bar, going until AK bar. Okay? The rest is 0. All right? So I have where, of course, this A bar, it can be written as P inverse AP. So the same formula here, the basis change formula. Okay? And this P matrix is composed of the basis vectors of these subspaces. So I have P1, P2. These are some columns, and I have some PK. P1, P2 contains the columns of the basis vectors of each of these subspaces. All right? And each of PI, each of these matrices would contain the basis vectors of the ith subspace, BI1, BI2, going until BINI. All right? So here, Ni is the dimension of the subspace Mi. Okay? And I is our dimension for the subspace. And BI1, BI2, going on until BI and I. Remember here, Ni is the dimension of the subspace Mi, and in this case, I would have Ni basis vectors for that subspace. Okay? These BI vectors are the basis vectors, for Mi. And finally, these AI bars, these blocks, they have the size Ni by Ni, is of size Ni by Ni. Okay? So remember here, in the earlier case, our blocks were 1 by 1 blocks. And in this case, you see that the dimension of these subspaces were actually 1. Okay? That is why we had a diagonal representation. All right? And remember, we formed the P matrix in this case, from the basis vectors of these null spaces. These were eigenspaces. Therefore, the basis vector for the first eigenspace was the first eigenvector, and basis vector for the second eigenspace was the second eigenvector. So we have formed our P matrix from the matrices P1 and P2. Each had a single column because the dimensions of these null spaces were both equal to 1. Okay? So now I'm actually going to try to prove this, but I won't give a proper proof. Okay? So I will give just a specific case, which is not an actual proof of the theorem. Okay? So therefore, this is only going to be a sketch of a proof, and I will tell you how to obtain the actual proof later. So, sketch of the proof. Okay? So I will just consider, so here the theorem is general. Okay? There are k subspaces here, and therefore, in order for me to be able to prove this theorem, I need to consider just k subspaces, a general number of subspaces. In the sketch of the proof, I will assume that there are only 2 subspaces. Okay? And because of that, this thing that I'm going to be writing won't be a correct proof of this theorem. Okay? For the correct proof, you have to generalize that proof idea to a general number of subspaces. Okay? So here, suppose that k equals to 2. As soon as I write k equals to 2, I'm finished, because this is not a proof anymore. This is not the proof of this general theorem anymore. It is a proof of the case k equals to 2. Therefore, by giving only the rest here, I won't be able to claim that this is the proof of the theorem. Okay? This is only the proof of the theorem for k equals to 2. Okay? So in order to be able to generalize this proof, to obtain a correct proof, you need to start with an arbitrary k. You cannot start with a specific k here. Okay? So here let us say that Cn is equal to m1 plus m2. Okay? Let me say that m1 is 2-dimensional and m2 is 3-dimensional. Okay? And then in a direct sum, then I know what the dimension here on the left should be. Okay? In a direct sum, dimension sums on the right should be equal to the dimension of the left-hand side. So dimension of this thing should be 5. But this is Cn. So what is n in this case? N should be 5. Okay? In this case. So that means that we have a 5 by 5 matrix, and these x and y vectors are vectors with 5 complex elements in general. Okay? So now let us come up with some basis vectors. So here A is an element of C5 by 5. Okay? And we have decomposed C5 into M1 and M2. Okay? And I have here this basis vectors for M1 and M2. Let us say that basis vectors for, let me say, M1 is, let us say, span of B11 and B12. These are the basis vectors of M1. And M2 is span of how many basis vectors? 3 basis vectors. B21, B22, and B23. Okay? These are the basis vectors of M2. And here I need to assume that M1 and M2 are invariant, are both invariant under A. Okay? So we have just this. Now I'm going to form my P matrix. Okay? Each of these vectors are in Cn. Okay? And I'm going to put them into a single P matrix. What should be the size of the P matrix? It is again going to be 5 by 5. Okay? I will put first the basis vectors of the first subspace, B11, B12, and these two columns would be my P1 matrix. Okay? P1 matrix would be composed of basis vectors of the subspace. This is my P1. Okay? And P2 is going to contain three columns, B21, B22, and B23. Okay? So each of these vectors are in C5, so this would be a 5 by 5 matrix, which is invertible in this case. Okay? And these three columns would form P2. All right? So I have this 5 by 5 P matrix, and I would like to find the A bar, which is the new representation. Okay? And P, remember, is the basis change matrix. So we would like to change the basis of this linear transformation into this set composed of 5 elements for Cn. Okay? C5. And we need to obtain this A bar. And we need to show that it is going to be block diagonal, and the blocks will have size 2 and 3. Okay? And how can we do that? We are going to use this equation. Okay? I'm going to use this equation here in order to be able to find A bar. And this is P, my basis change matrix composed of the basis vectors of these invariant subspaces. Okay? So remember here in this formula I have P inverse. So in order to be able to find A bar, do I need to calculate the inverse of this matrix? In order to be able to find A bar, do I need to calculate the inverse of this matrix, which is unknown now? I didn't give any numbers here. So the answer is going to be no. Instead, we are going to use this equation in another form. All right? So here, A bar is P inverse AP. I will take this P inverse to the left-hand side by multiplying both sides by P from the left. Okay? So this is going to give me P times A bar. P and P inverse would be identity, and I would have AP. And in this equation, you see that there is no P inverse anymore. Okay? So we will always use this equation P containing P inverse AP in this form. P times A bar is A times P. Okay? And in this formula, there is no P inverse, so we won't need to invert this matrix. So now let us try to write this P here. P is those 5 columns, B11, B12, B21, B22, B23, times A bar. A bar is this matrix, okay? And that is equal to A times P. So I need to write the same matrix once more. B11, B12, and I would have B21, B22, B23. Okay? So this is my P again, AP, and this is my P, and this is A bar that I need to find. How can I show that this A bar is going to have a block diagonal structure like this, with 2 blocks corresponding to each subspace, with sizes 2 by 2 and with sizes 3 by 3? Okay? So for that, I'm first going to look at the right-hand side. This A is multiplied by the P matrix with these columns. Okay? So if I use the rules of matrix multiplication, I can see that the first column of the multiplication is going to be A times B11. This is the first column of the multiplication. What is the second column of the multiplication? A times B12, A times the second column. Third column is A times B21. Fifth, A times B22. And I'm sorry, I need to erase this. So I have C2 is M1 plus M2, this is 2, this is 3. And I have here just this thing, A times B2, 3. Okay? This is the multiplication of this matrix times a partition matrix with columns. Okay? A times B11, A times B22, etc. Each column is multiplied with A. So now what do I have to do? So in order to be able to find the first column of A bar, I need to look at the first column of the right-hand side. First column of the right-hand side is A times B11, okay? And in order to be able to find the first column of the, so the first column of the multiplication should be AB11, okay? So, you know, and I need to write AB11 as a linear combination of the columns of P here, and the coefficients of that linear combination is going to be the first column of A bar. I need, in order to be able to find the first column of A bar, I need to express the first column of the right-hand side as a linear combination of the columns of P. And then I have 5 columns. I need to put these 5 coefficients here into the first column of A bar. Okay? Because here the first column of this multiplication would be the first column of A bar multiplied by P. So the first element multiplied by B11, the second element multiplied by B12, and then summed. And third element times this, fourth element times this, fifth element times this, and sum. That is going to be the overall first column of that multiplication. Okay? So now is the time to use the invariance property of the subspaces. Okay? How can I use this invariance? I know that M1 is invariant under A. So the first basis vector is an element of M1. Okay? So if M1 is invariant under A, then A times the first basis vector here would be also in M1. Okay? If M1 is invariant, when I take any vector in M1 and when I transform it with A, I need to obtain another vector in M1. Okay? That is the meaning of invariance. The first basis vector is, of course, in M1 because it's a basis vector of M1. Okay? And when I multiply this first basis vector with A, I am obviously going to obtain a vector in M1 because M1 is invariant under A. Okay? So here this first column of the matrix is nothing but B11, the first basis vector, multiplied by A. And therefore this multiplication, because M1 is invariant under A, should be an element of M1. And any element of M1 can be written as a linear combination of its basis vectors. Okay? So that means that this first column, I can express it as a linear combination of those columns. I can express it as a linear combination of only these 2 columns. Okay? So this first column can be expressed as a linear combination of only these 2 columns. And then what would be the coefficients of the next 3 columns here? They should be equal to 0. Okay? So I need to have here alpha 1, 1 and alpha 1, 2. These are the coefficients of AB11, which should be inside M1 and which can be expressed as a linear combination of these 2 columns only. These are going to be the coefficients expressing this vector as a linear combination of B11 and B12. And the rest of the coefficients should be 0. Okay? That is a very important conclusion here. What about the second column? In that case, I have this vector, the second basis vector of M1 times A. In order to be able to find the second column of A bar, I need to express this second column here as a linear combination of these vectors, these columns of P, and I need to write the coefficients here into the second column of A bar. Okay? B12 is an element of M1, and therefore AB12 is always going to be M1 still. Why is that? Because M1 is invariant under A. If I take any vector in M1, if I multiply it with A, then the result should be inside M1 because M1 is invariant under A. Okay? So if I try to express AB12, which is in M1 as a linear combination of those columns, only the first two coefficients can be non-zero. The last three coefficients will be always equal to 0. Okay? So I would have here beta 1, 1, beta 1, 2, and I would have 0, 0, 0 here. So you see here our first 2 by 2 block. Okay? Let us go into the third column. The third column is AB21. B21 is an element of M2, and M2 is invariant under A. As a result, AB21 should be inside M2 still because of the invariance. As a result, if I try to express AB21 as a linear combination of these columns, only the last three coefficients can be non-zero. The first two coefficients should be always equal to 0. Okay, so I would have 0, 0, alpha 2, 1, alpha 2, 2, alpha 2, 3. Okay? Sometimes these coefficients can also be non-zero, but we don't know currently because everything is unknown. Okay? These coefficients can also be sometimes 0. Okay? For example, the first coefficient might be 0, of course. The other ones can be non-zero. Okay? But the only thing from this set of information I can get is that the first two coefficients will be always 0 because AB21 is always inside M2, which is a linear combination of these last three vectors, basis vectors of M2. So similarly, I can continue the fourth and the fifth columns like this. Okay? This is in M2. As a result, the coefficients expressing this fourth column as a linear combination of these vectors would be 0, 0, beta 2, 1, beta 2, 2, and beta 2, 3. And the last column is also inside M2 because of the invariance, and therefore the coefficients should be gamma 2, 1, gamma 2, 2, gamma 2, 3. Okay? So you see now that because of these 0 elements, I have a block diagonal A bar matrix. And I see here that the first block has size 2 by 2, and the second block has size 3 by 3. And the dimension of M1 was 2, and the dimension of M2 is equal to 3. Okay? So dimensions of these, sizes of these blocks are related to the dimensions of the invariant subspaces. And this block diagonal property is coming from the invariance properties of these subspaces. Okay? So this is just the proof of this theorem for the case k equals to 2. In order to be able to prove this theorem, this is not an actual proof, as I told you. In order to be able to prove this theorem, you have to generalize this idea to an arbitrary k. Okay? So you would start with k subspaces, invariant subspaces, and then you would hear k basis sets, an arbitrary number of basis sets, of course. Here I have selected the basis sets to be composed of 2 and 3 elements. But in the theorem, the number of base elements should be n1, a general number, and this should be n2, not 3. So these specific selections also they also make the statements that I write here not a proof, actually, not a general correct proof. So for the general proof, you have to generalize this proof idea for an arbitrary number of subspaces with an arbitrary number of basis elements. Okay? But this is the sketch of the proof. You have to repeat this for the general quantities. So now let us look at an example. So in the example, I will have a 3 by 3 matrix. A is given by a 3 by 3 matrix, and the matrix is this: 1, minus 1, 0, 1, 3, 0, minus 1, minus 2, 1. And I will define M1 subspaces, span of 1, 1, 0 and 0, 1, 0. And I would have M2 is span of 0, 1, 1. Okay? So now with this A matrix and with these subspaces, we are going to ask some questions. So what is the dimension of M1 in this case? The number of linearly independent basis vectors, of course basis vectors are linearly independent. The number of basis vectors is 2, so M1 is 2-dimensional. So dimension of M1 is 2, and dimension of M2 is just 1, because it has one basis vector. Okay? So now I will ask, the first question that I'm going to be asking is this one. Is M1 invariant under A? Okay? That is our first question. The second question will be, is M2 invariant under A? And then we are going to look at their sum. So now, in order to be able to understand if M1 is invariant under A, I need to show that when I take any vector in M1, in this span, when I transform it with A, I would always obtain another vector in M1. Okay? That is the invariance question. So here is what I'm going to do. I will first name these basis vectors. So this is B11 and this is B12. Let us say that this is B21. Okay? So now I'm going to look at A times B11. The first basis vector times A. Okay? I will check if when I multiply when I transform the first basis vector with A, then am I going to get another vector inside M1 or not? Okay? That is going to be, if I again obtain another vector inside M1, then we are fine. If the new vector is not in M1 anymore, then M1 cannot be invariant under A. I will check each of these basis vectors, multiply each of these basis vectors with A, and then I will check if the results are still in M1 or not. If they are, if all of them are in M1, then M1 is invariant under A. If at least one of them is not in M1, then M1 cannot be invariant. A times B11, this matrix times 1, 1, 0. When you multiply a matrix with a column vector 1, 1, 0, that means that you need to multiply its first column with 1, the second column with 1, and the third column with 0, and then sum the resulting vectors. So multiplying A with the vector 1, 1, 0 means that you need to sum the first two columns and forget about the third one. Okay? So I'm summing the first two columns. It's going to give me 2 times 2, and 0. Okay? Do you think this vector is in M1 still? This new vector, A times B11, is inside M1 or not? The question is, can I write this vector as a linear combination of these two basis vectors? Any vector inside M1 can be written as a linear combination of these two vectors, basis vectors. Okay? So this 2, 2, 0, of course, can be written as a linear combination of these two vectors. Okay? And it is 2 times B11 plus 0 times B12. Okay? And you see that because this vector is a linear combination of the basis vectors, it is inside this span. That means this vector is in M1. Okay? So now let us look at A times B12, the second basis vector of M11. When you multiply this square matrix with the vector 0, 1, 0, this means that you need to take the second column. Okay? So what is the second column of A? 1, 3, and 0. Okay? And now the question is, can you write this vector as a linear combination of B11 and B12? That is what being inside M1 means. This is equal to B11 times B11 and B12. Can you find coefficients here and here which would satisfy, which will make the result 1, 3, 0? Okay? Yes, the result is yes. If I multiply B11 with 1, and if I multiply B12 with 2, when I sum them, you see that I obtain 1, 3, 0. Okay? That means that this vector is inside M1 as well. Okay? So since both of the basis vectors, when they are transformed with A, the results are inside M1, then M1 is invariant under A. M1 is invariant under A. Okay? So here I will ask you a question from these results. One of these basis vectors is an eigenvector of the matrix A. Which one do you think it is? One of these vectors, B11 and B12, is an eigenvector of A. Which basis vector is an eigenvector and which basis vector is not? So here you see that A times B11 is 2B11. Okay? So this B11 is satisfying an eigenvector equation. AE1 is equal to 2E1. Okay? So B11 is an eigenvector corresponding to the eigenvalue 2. I have learned that this matrix, with this equation, I have learned that this matrix has an eigenvalue at 2, and the corresponding eigenvector, a corresponding eigenvector, is B11. What about B12? B12 is not really an eigenvector. Okay? It is A times B12 should be lambda times B12 for B12 to be an eigenvector. And you see that A times B12 is 2 times B12 plus something, some non-zero quantity. So this means that this B12 is not really an eigenvector. But B11 is an eigenvector, and its eigenvalue is just 1, is just 2. Okay? It is this number. So now let us ask the second question. Is M2 invariant under A? Under A. That is our second question. M2 is a one-dimensional subspace, and therefore it has only a single basis vector. So now, in order to be able to understand if it is invariant or not, I'm going to ask the same question. A times the basis vector, B21, what is this? So when I multiply a matrix with the vector 0, 1, 1, this means that I need to sum the last two columns. Okay? The result is, if I sum the last two columns, I would have 0, 1, 1. Okay? The question is this vector inside M2? I have started with a basis vector in M2, and I transformed it with A. Is the result inside M2? This is already the same as the basis vector. So this is 1 times the basis vector 0, 1, 1. It is 1 times B21. That means that this is inside M2. Okay? So this actually makes M2 invariant. M2 is invariant under A. Okay? So I have learned that these two subspaces are invariant under A. And here I can ask you again a question. Is B21 an eigenvector? Is B21 an eigenvector? The answer is again yes. A times B21 is 1 times B21. That means that B21 is an eigenvector corresponding to the eigenvalue 1. Okay? That actually says this. So both of these subspaces are invariant under A. What happens when I sum these two subspaces, M1 plus M2? This sum is the set of vectors which can be written as the sum of two vectors, one from M1 and another one from M2. Okay? When I sum, so what type of vectors can be written as the sum of two vectors? One from M1, which is a linear combination, which can be a linear combination of these two vectors, an arbitrary linear combination, and another one from M2, a linear combination of this single vector. Okay? So you will see that if you think about this, these two vectors and these three vectors are all linearly independent. So in order to be, so the sum is actually going to be any vector in C3. Or you can write R3 if you want to use real coefficients only. Okay? So C3 can be written as a sum of M1 and M2. Is this sum a direct sum? Or I can ask the equivalent question, are M1 and M2 linearly independent? That is our question. And if you look at these basis vectors, you see that I cannot write the basis vector of M2 as a linear combination of these two vectors, as a linear combination of the basis vectors of M1. As a result, M1 and M2 are actually linearly independent, making this a direct sum. Okay? So you see that I could write C3 as a linear combination of two subspaces, as a direct sum of two subspaces. And these two subspaces are invariant under A, and they have dimensions 2, 1, and this is 3. And M1 and M2 are invariant under A. Okay? As a result, if I form a P matrix which is composed of columns which are the basis vectors of these subspaces, I can obtain a simplified matrix representation, a block diagonal representation with blocks with sizes 2 and 1. Okay? Let us now try to do that. So I will first select my P matrix. So P is going to be selected out of the basis vectors of these subspaces, M1 and M2. Basis vectors of M1 would be 1, 1, 0 and 0, 1, 0 here. And I would have M2 is 0, 1, 1. So this is my P1 matrix, this 3 by 2 matrix, and this is my P2 matrix. Okay? Composed of the basis vectors of these subspaces. All right? Now let us use our equation. P times A bar is A times P. Now here is what I'm going to do. So this is B11, B12, B11, B12, and I have B21. This is my P times A bar is equal to A times B11, B12, and B21. Okay? So I have P here. So this is the equation. A bar is equal to P inverse AP. Okay? So now I need to find what this A bar is. Okay? And in order to be able to find that, I'm going to apply the same procedure. This right-hand side is A times B11, A times B12, A times B21. Okay? And if I express A times B11 as a linear combination of these columns, then I will find the first column of A bar by using the coefficients of that linear combination. Okay? A times B11, A times B11, if it is inside still M1, okay? Because B11 is a basis vector of M1, and as a result, when I transform B11 with A, the result is going to be still in M1. As a result, I can express the result as a linear combination of the first two columns here. And the third column coefficient is going to be 0. Okay? So here, I have selected this P, but I have used this B11, B22 here. Why did I do that? Instead here I could have written those actual P values here, and I would have made the same calculations, but we have already did those calculations, okay? A times B11 is 220, and if I try to write it as a linear combination of these three vectors, I know that I have the coefficients 2, 0, and the third coefficient is going to be 0, okay? So I have 2, 0, 0. 2 times B11, 0 times B12, plus 0 times B21. Okay? This is already in this equation that I have written there. And what about A, B12? Okay? It is going to be A times this vector, the second column, and if I try to express it as a linear combination of the columns of P, then I'm going to obtain 1 times the first basis vector, first column, 2 times the second column, plus 0 times the third column. Okay? So I have 1, 2, and 0. 1, 2, and 0. Because it is already inside M1. So this is my first 2 by 2 block. And what about the 1 by 1 block at the end? So in this case, A times B21, it is A times B21 is already equal to B21. Okay? As a result, it is inside M2, and this is, the coefficients should be 0, 0, 1. Okay? So our neo A bar is going to be in the following form: 2, 2, 1, 1, 0, 0, 0, 0. So you see it is a block diagonal, and the blocks have sizes 2 and 1, which are the dimensions of these subspaces. So in this case, A1 bar is a 2 by 2 block given like this. A2 bar is equal to 1, which is a 1 by 1 block. And the interesting thing is actually this matrix is a non-diagonalizable matrix. And as a result, you cannot find subspaces, invariant subspaces, which would diagonalize this matrix, which would simplify this matrix into a diagonal representation. Okay? But this matrix, of course, is not diagonalizable, but it has a Jordan canonical form, which is the closest form to the diagonal that we can obtain for any matrix. And actually, this form is the so-called Jordan canonical form for that matrix. Okay, so we have as many zeros as possible here, and the matrix is close to diagonal matrix as possible. Okay. So now we are going to learn in the rest of the course actually how we can obtain these subspaces, using which we can obtain some basis sets that would simplify the matrices into their simple matrix representations. Okay? And why do we do that? Because if we can simplify the matrix, and if we look at it as simple form, simple representation, we would understand much more about what that matrix or what that linear transformation is doing. Okay? But these are for the next and coming courses. That's all for this lecture. Thank you for watching.